Let's do some more of section 3.5, implicit differentiation. Kind of as a warm-up, I want you to think about these three problems at the top. The derivative with respect to x of x squared, the derivative with respect to y of y squared, and the derivative with respect to x of y squared. Take a moment and think about the answers for each one of those. I assume everybody got 2x for the first one, 2y for the second one. But the third one, the idea here is y is implicitly a function of x. So there's an outside function, squared function, and an inside function, y. So the answer is the derivative of the outside function by the chain rule, which is just the derivative of y squared with respect to y, which we got over here in the second one of these. That goes here. That's the derivative of the outside function. Now we need the derivative of the inside function, which is dy dx. And it's fine to write that as 2y prime. But when you write primes, you have to, it's hidden what the independent variable is. That's why I like this other notation, dy dx, better. Because later on we'll take derivatives with respect to time or x, and the independent variable might change. Okay, so say we're given 2x squared plus xy minus y squared equal 2. And we want to find the derivative of y with respect to x. That's the instantaneous rate of change of y with respect to x by implicit differentiation. And again, recall that the graph of an equation in two variables is just some curve in the plane. Now I could go to Desmos and figure out what curve that is, but it's going to be some kind of curve in the plane. And I'm just making up a curve. And remember, the idea here is this curve implicitly defines lots of functions. I could go from here to here around the bottom piece of this curve. And this piece passes the vertical line test. So this is a function that's buried inside or implicitly defined by this equation, 2x squared plus xy minus y squared equal 2. When you use implicit differentiation, you find the slope of the tangent line for any of these implicitly defined functions, for any pieces of the graph that do pass the vertical line test. Okay, first step of implicit differentiation, recall you're just given an equation in x and y, is to take the derivative of both sides. And I know the independent variable is x and the dependent variable is y because I'm finding derivative of y with respect to x. This tells me that y is the dependent variable, x is the independent variable. I want to take derivatives of both sides with respect to x. And when I use implicit differentiation, my mindset has got to be y is implicitly a function of x. Okay, the derivative of a sum is the sum of the derivatives. Same thing for a difference. and the derivative of the constant 2 is 0. Okay, so I get 4x plus, now, derivative with respect to x of x times y. Neither one of these is a constant because y is implicitly a function of x. So I've got a product. I've got to use product rule, which is the first times the derivative of the second. All I can say is dy dx, derivative of y with respect to x, plus the second times the derivative of the first. But the derivative of x with respect to x is 1. Again, I just used product rule for derivative with respect to x of xy. Now, derivative with respect to x of y squared. Y is a function of x. So this is really like if I had f of x squared. Okay, I'd have to use chain rule to find the derivative of that. Take the derivative of the outside. Power rule, you get 2y to the first, multiply by the derivative of the inside. Okay, the calculus is done. It's algebra from here on out. I want terms with dy dx, I want them moved to the left. Terms without dy dx, them moved to the right. But let's get rid of these parentheses. I'm just adding, so I can just remove the parentheses. Okay. Any term with dy dx, I'm leaving it on the left. Any term without dy dx, I'm moving it to the other side. To undo adding 4x, I subtract 4x. To undo adding y, I subtract y. Now, I want dy dx written just once. So, I factor out a dy dx. And I have left x minus 2y. If you multiply x minus 2y by dy dx, you get this left-hand side of the equation up here. X dy dx minus 2y dy dx. Okay. Now, this is dy dx times x minus 2y. It's not derivative of x minus 2y. It's derivative of y with respect to x times x minus 2y. To undo this multiplication by x minus 2y, I divide both sides by x minus 2y. So this is what I get. Your answer might be 4x plus y times negative x plus 2y. That's equivalent. Notice I'm just multiplying numerator and denominator by negative 1. So I'm just multiplying by 1. Or that's the same as derivative of y with respect to x is 4x plus y over 2y minus x. 3 different ways of writing the same answer. If I had a point, a value of x, a value of y, I could plug them in here for x and y and get the slope of the tangent line at that point. If you have questions, send me an email. Okay, let's do this one. Cosine xy equal 1 plus sine y. Let's find the derivative of y with respect to x by implicit differentiation. So I take derivatives of both sides with respect to x. The derivative of cosine is negative sine. That's the outside function. But I've got to multiply by the derivative of the inside function. Cosine xy is a composite function, so I had to use chain rule. Derivative of the outside is negative sine xy. Derivative of the inside is the derivative of xy. I'll just leave that and figure out what that is on the next line. I don't want to do too many steps at once and make errors. Okay, derivative of a sum is the sum of the derivatives. Okay. So the derivative with respect to x of xy, I need product rule. That's a product. So first times derivative of the second plus second times the derivative of the first. Product rule. Equals, the derivative of 1 is 0. The derivative with respect to x of sine y. Now remember, y is a function of x. So I've got an outside function and an inside function. The derivative of the outside is cosine y. The derivative of the inside is dy dx. Now I realize some of you prefer to write this. Negative sine xy. xy prime plus y equal cosine y, y prime. That's okay. The book does that. Webasine does that. But you really have to realize your independent variable's x. Again, I prefer this, but you can do the prime. But you really need to be writing this step like this, because it forces you to think about what the independent variable is. If you'll notice your Webasine, always when you do the watch it, they'll actually write this derivative on this second line like this, derivative with respect to x. Okay, now I'm solving for this dy dx or this y prime, whichever you want to use. But it's trapped inside some parentheses. It's trapped inside these parentheses. So I've got to distribute negative sine xy times x dy dx minus sine xy times y. I just distributed negative sine xy across these parentheses. So I had to multiply by x dy dx plus y. So I've got cosine y dy dx on the right. Stop for just a minute and let you look at that. Be thinking of what questions you have. I now want to write terms with dy dx on the left, terms without dy dx on the right. So I'll bring this minus sine xy times y over to the right. So I'll add sine xy times y. Now I'll subtract cosine y dy dx from both sides to get that term on the left. Again, I want terms with dy dx on the left. And I'm going to say y sine xy. We usually like simpler things out front. Now, by the way, here on down is just algebra. These last 3 lines have just been algebra. I'm done with the calculus. What I'm doing is I'm solving for the symbol derivative of y with respect to x using algebra. This is really algebra 1, just solving a linear equation for a variable. dy dx is written twice. I want to write it just once. So factor out dy dx. And I'm going to write this as negative sine, or negative x sine xy. Again, we write simpler things out front. Minus cosine y. When you multiply negative x sine xy minus cosine y times dy dx, you get this left-hand side here. Give you a minute to look at that and make sure you agree. Okay, on the right-hand side, I've got y sine xy. So I've got dy dx times something. So to undo that multiplication, to solve for dy dx, I divide both sides by negative x sine xy minus cosine y. This is my answer. That could be written as negative y sine xy over x sine xy plus cosine y. There might be a temptation to cancel. Remember, you can't cancel unless you factor. You can't cancel here. Okay, before you view the next pencast, or the next file, or follow the next instruction, try for yourself, find dy dx by implicit differentiation if y cosine x equals x squared plus y squared. Do this number 11 here on page 215, section 3.5. Do it before looking at doing the next step.